0 is direct, A is above, but the index for way 1 is formed with a hash function. A good hash function has the property that addresses which conflict with the direct mapping tend not to conflict when mapped with the hash function, and so it is less likely that a program will suffer from an unexpectedly large number of conflict misses due to a pathological access pattern. The downside is extra latency from computing the hash function. 13. Additionally, when it comes time to load a new line and evict an old line, it may be difficult to determine which existing line was least recently used, because the new line conflicts with data at different indexes in each way. LRU tracking for non-skewed caches is usually done on a per set basis. Nevertheless, skewed associative caches have major advantages over conventional set associative ones. 14. Pseudo-associative cache. A true set associative cache tests all the possible ways simultaneously, using something like a content-addressable memory. A pseudo-associative cache tests each possible way one at a time. A hash-rehash cache and a column-associative cache are examples of a pseudo-associative cache. In the common case of finding a hit in the first way tested, a pseudo-associative cache is as fast as a direct mapped cache, but it has a much lower conflict miss rate than a direct mapped cache, closer to the miss ratio for fully associative cache. 13. Cache entry structure. Cache row entries usually have the following structure: tag, data block, flag bits. The data block, cache line, contains the actual data fetched from the main memory. The tag contains, part of, the address of the actual data fetched from the main memory. The flag bits are discussed below. The size of the cache is the amount of main memory data it can hold. This size can be calculated as the number of bytes stored in each data block times the number of blocks stored in the cache. The tag, flag and a correction code bits are not included in the size. 15, although they do affect the physical area of a cache. An effective memory address which goes along with the cache line, memory block, is split, MSB to LSB, into the tag, the index and the block offset. 16. 17. Tag index block offset. The index describes which cache set that the data has been put in. The index length is bits for scarce sets. The block offset specifies the desired data within the stored data block within the cache row. Typically the effective address is in bytes, so the block offset length is bits, where B is the number of bytes per data block. The tag contains the most significant bits of the address, which are checked against all rows in the current set. The set has been retrieved by index, to see if this set contains the requested address. If it does, a cache hit occurs. The tag length in bits is as follows: tag underscore length equals address underscore length, index underscore length, block underscore offset underscore length. Some authors refer to the block offset as simply the offset, 18, or the displacement. 19, 20. Example. The original Pentium 4 processor had a 4-way set associative L1 data cache of 8 KB in size, with 64-byte cache blocks. Hence, there are 8 KB/64 equals 128 cache blocks. The number of sets is equal to the number of cache blocks divided by the number of ways of associativity, what leads to 128/4 equals 32 sets, and hence 25 equals 32 different indices. There are 26 equals 64 possible offsets. Since the CPU address is 32 bits wide, this implies 32 to 5. 6 equals 21 bits for the tag field. The original Pentium 4 processor also had an 8-way set associative L2 integrated cache 256 KB in size, with 128-byte cache blocks. This implies 32 to 8, 7 equals 17 bits for the tag field. 18. Flag bits. An instruction cache requires only one flag bit per cache row entry, a valid bit. The valid bit indicates whether or not a cache block has been loaded with valid data. On power up, the hardware sets all the valid bits in all the caches to invalid. Some systems also set a valid bit to invalid at other times, such as when multi-master bus snooping hardware in the cache of one processor hears an address broadcast from some other processor, and realizes that certain data blocks in the local cache are now stale and should be marked invalid. A data cache typically requires 2 flag bits per cache line, a valid bit and a dirty bit. Having a dirty bit set indicates that the associated cache line has been changed since it was read from main memory. Dirty, meaning that the processor has written data to that line and the new value has not propagated all the way to main memory. Cache miss. A cache miss is a failed attempt to read or write a piece of data in the cache, which results in a main memory access with much longer latency. There are 3 kinds of cache misses: instruction read miss, data read miss, and data write miss. Cache read misses from an instruction cache generally cause the largest delay, because the processor, or at least the thread of execution, has to wait, stall, until the instruction is fetched from main memory. Cache read misses from a data cache usually cause a smaller delay, because instructions not dependent on the cache read can be issued and continue execution until the data is returned from main memory, and the dependent instructions can resume execution. Cache write misses to a data cache generally cause the shortest delay, because the write can be queued and there are few limitations on the execution of subsequent instructions. The processor can continue until the queue is full. For a detailed introduction to the types of misses, see cache performance measurement and metric. Address translation. Most general-purpose CPUs implement some form of virtual memory. To summarize, either each program running on the machine sees its own simplified address space, which contains code and data for that program only, or all programs run in a common virtual address space. A program executes by calculating, comparing, reading and writing to addresses of its virtual address space, rather than addresses of physical address space, making programs simpler and thus easier to write. Virtual memory requires the processor to translate virtual addresses generated by the program into physical addresses in main memory. The portion of the processor that does this translation is known as the Memory Management Unit, MMU. The fast path through the MMU can perform those translations stored in the Translation Look-Aside Buffer, TLB, which is a cache of mappings from the operating system's page table segment table, or both. For the purposes of the present discussion, there are 3 important features of address translation latency. The physical address is available from the MMU sometime, perhaps a few cycles after the virtual address is available from the address generator. Aliasing. Multiple virtual addresses can map to a single physical address. Most processors guarantee that all updates to that single physical address will happen in program order. To deliver on that guarantee, the processor must ensure that only one copy of a physical address resides in the cache at any given time. Granularity. The virtual address space is broken up into pages. For instance, a 4 GB virtual address space might be cut up into 1,048,576 pages of 4 KB size, each of which can be independently mapped. There may be multiple page sizes supported. See virtual memory for elaboration. Some early virtual memory systems were very slow because they required an access to the page table, held in main memory, before every programmed access to main memory. NB1, with no caches. This effectively cut the speed of memory access in half. The first hardware cache used in a computer system was not actually a data or instruction cache, but rather a TLB. 22. Caches can be divided into 4 types, based on whether the index or tag correspond to physical or virtual addresses: physically indexed, physically tagged, pipped, caches use the physical address for both the index and the tag. While this is simple and avoids problems with aliasing, it is also slow, as physical address must be looked up, which could involve a TLB miss and access to main memory, before that address can be looked up in the cache. Virtually indexed, virtually tagged, VIVD, caches use the virtual address for both the index and the tag. This caching scheme can result in much faster lookups, since the MMU does not need to be consulted first to determine the physical address for a given virtual address. However, VIVD suffers from aliasing problems, where several different virtual addresses may refer to the same physical address. The result is that such addresses would be cached separately despite referring to the same memory, causing coherency problems. Although solutions to this problem exist, 23, they do not work for standard coherence protocols. Another problem is homonyms, where the same virtual address maps to several different physical addresses. It is not possible to distinguish these mappings merely by looking at the virtual index itself, though potential solutions include flushing the cache after a context switch, forcing address spaces to be non-overlapping, tagging the virtual address with an address space ID, ACID. Additionally, there is a problem that virtual to physical mappings can change, which would require flushing cache lines, as the VAS would no longer be valid. All these issues are absent if tags use physical addresses, VIPD. Virtually indexed, physically tagged, VIPD, caches use the virtual address for the index and physical address in the tag. The advantage over PIPD is lower latency, as the cache line can be looked up in parallel with the TLB translation. However, the tag cannot be compared until the physical address is available. The advantage over VIVD is that since the tag has the physical address, the cache can detect homonyms. Theoretically, VIPD requires more tag bits because some of the index bits could differ between the virtual and physical addresses, for example bit 12 and above for 4 KB pages, and would have to be included both in the virtual index and in the physical tag. In practice, this is not an issue because, in order to avoid coherency problems, VIPD caches are designed to have no such index bits, for example, by limiting the total number of bits for the index and the block offset to 12 for 4 KB pages. This limits the size of VIPD caches to the page size times the associativity of the cache. Physically indexed, virtually tagged, PIVD, caches are often claimed in literature to be useless and non-existing. 24. However, the MIPS R6000 uses this cache type as the Solinome implementation. 25. The R6000 is implemented in emitter-coupled logic, which is an extremely fast technology not suitable for large memories such as a TLB. The R6000 solves this issue by putting the TLB memory into a reserved part of the second-level cache, having a tiny, high-speed TLB slice on chip. The cache is indexed by the physical address obtained from the TLB slice. However, since the TLB slice only translates those virtual address bits that are necessary to index the cache and does not use any tags, false cache hits may occur, which is solved by tagging with the virtual address. The speed of this recurrence, the load latency, is crucial to CPU performance, and so most modern level 1 caches are virtually indexed, which at least allows the MMU's TLB lookup to proceed in parallel with fetching the data from the cache RAM. But virtual indexing is not the best choice for all cache levels. The cost of dealing with virtual aliases grows with cache size, and as a result most level 2 and larger caches are physically indexed. Caches have historically used both virtual and physical addresses for the cache tags, although virtual tagging is now uncommon. If the TLB lookup can finish before the cache RAM lookup, then the physical address is available in time for tag compare, and there is no need for virtual tagging. Large caches, then tend to be physically tagged, and only small, very low latency caches are virtually tagged. In recent general-purpose CPUs, virtual tagging has been superseded by VINs, as described below. Homonym and synonym problems. A cache that relies on virtual indexing and tagging becomes inconsistent after the same virtual address is mapped into different physical addresses, homonym, which can be solved by using physical address for tagging, or by storing the address space identifier in the cache line. However, the latter approach does nothing against the synonym problem, in which several cache lines end up storing data for the same physical address. Writing to such locations may update only one location in the cache, leaving the others with inconsistent data. This issue may be solved by using non-overlapping memory layouts for different address spaces, or otherwise the cache, or a part of it, must be flushed when the mapping changes. 26. Virtual tags and VINs. The great advantage of virtual tags is that, for associative caches, they allow the tag match to proceed before the virtual to physical translation is done. However, coherence probes and evictions present a physical address for action. The hardware must have some means of converting the physical addresses into cache index, generally by storing physical tags as well as virtual tags. For comparison, a physically tagged cache does not need to keep virtual tags, which is simpler. When a virtual to physical mapping is deleted from the TLB, cache entries with those virtual addresses will have to be flushed somehow. Alternatively, if cache entries are allowed on pages not mapped by the TLB, then those entries will have to be flushed when the access rights on those pages are changed in the page table. It is also possible for the operating system to ensure that no virtual aliases are simultaneously resident in the cache. The operating system makes this guarantee by enforcing page coloring, which is described below. Some early RISC processors, SPARC, RS/6000, took this approach. It has not been used recently, as the hardware cost of detecting and evicting virtual aliases has fallen and the software complexity and performance penalty of perfect page coloring has risen. It can be useful to distinguish the two functions of tags in an associative cache. They are used to determine unique way of the entry set to select, and they are used to determine if the cache hit or missed. The second function must always be correct, but it is permissible for the first function to guess, and get the wrong answer occasionally. Some processors, for example early SPARCs, have caches with both virtual and physical tags. The virtual tags are reused for way selection, and the physical tags are used for determining hit or miss. This kind of cache enjoys latency advantage of a virtually tagged cache, and the simple software interface of a physically tagged cache. It bears the added cost of duplicated tags, however. Also, during misprocessing, the alternate ways of the cache line indexed have to be probed for virtual aliases and any matches evicted. The extra area, and some latency, can be mitigated by keeping virtual hints with each cache entry instead of virtual tags. These hints are a subset or hash of the virtual tag, and are used for selecting the way of the cache from which to get data and a physical tag. Like a virtually tagged cache, there may be a virtual hint match but physical tag mismatch, in which case the cache entry with the matching hint must be evicted so that cache accesses after the cache fill at this address will have just one hint match. Since virtual hints have fewer bits than virtual tags distinguishing them from one another, a virtually hinted cache suffers more conflict misses than a virtually tagged cache. Perhaps the ultimate reduction of virtual hints can be found in the Pentium 4, Willamette and Northwood cores. In these processors the virtual hint is effectively 2 bits, and the cache is 4-way set associative. Effectively, the hardware maintains a simple permutation from virtual address to cache index, so that no content addressable memory, CAM, is necessary to select the right one of the 4 ways fetched. Page coloring. Large physically indexed caches, usually secondary caches, run into a problem. The operating system rather than the application controls which pages collide with one another in the cache. Differences in page allocation from one program run to the next lead to differences in the cache collision patterns, which can lead to very large differences in program performance. These differences can make it very difficult to get a consistent and repeatable timing for a benchmark run. To understand the problem, consider a CPU with a 1 MB physically indexed direct mapped level 2 cache and 4 KB virtual memory pages. Sequential physical pages map to sequential locations in the cache until after 256 pages the pattern wraps around. We can label each physical page with a color of 0255 to denote where in the cache it can go. Locations within physical pages with different colors cannot conflict in the cache. Programmers attempting to make maximum use of the cache may arrange their program's access patterns so that only 1 MB of data need be cached at any given time, thus avoiding capacity misses. But they should also ensure that the access patterns do not have conflict misses. One way to think about this problem is to divide up the virtual pages the program uses and assign them virtual colors in the same way as physical colors were assigned to physical pages before. Programmers can then arrange the access patterns of the code so that no two pages with the same virtual color are in use at the same time. There is a wide literature in such optimizations, for example loop nest optimization, largely coming from the High Performance Computing (HPC) community. The snag is that while all the pages in use at any given moment may have different virtual colors, some may have the same physical colors. In fact, if the operating system assigns physical pages to virtual pages randomly and uniformly, it is extremely likely that some pages will have the same physical color, and then locations from those pages will collide in the cache. This is the birthday paradox. The solution is to have the operating system attempt to assign different physical color pages to different virtual colors, a technique called page coloring. Although the actual mapping from virtual to physical color is irrelevant to system performance, odd mappings are difficult to keep track of and have little benefit, so most approaches to page coloring simply try to keep physical and virtual page colors the same. If the operating system can guarantee that each physical page maps to only one virtual color, then there are no virtual aliases, and the processor can use virtually indexed caches with no need for extra virtual alias probes during mishandling. Alternatively, the OS can flush a page from the cache whenever it changes from one virtual color to another. As mentioned above, this approach was used for some early SPARC and RS/6000 designs. Cache hierarchy in a modern processor. Memory hierarchy of an AMD Bulldozer server. Modern processors have multiple interacting on-chip caches. The operation of a particular cache can be completely specified by the cache size, the cache block size, the number of blocks in a set, the cache set replacement policy, and the cache write policy, write through or write back. 18. While all of the cache blocks in a particular cache are the same size and have the same associativity, typically lower-level caches, called Level 1 cache, have a smaller number of blocks, smaller block size, and fewer blocks in a set, but have very short access times. High-level caches, i.e. Level 2 and above, have progressively larger numbers of blocks, larger block size, more blocks in a set, and relatively longer access times, but are still much faster than main memory. Cache entry replacement policy is determined by a cache algorithm selected to be implemented by the processor designers. In some cases, multiple algorithms are provided for different kinds of workloads. Specialized caches. Pipeline CPUs access memory from multiple points in the pipeline. Instruction fetch, virtual to physical address translation, and data fetch, See classic RISC pipeline. The natural design is to use different physical caches for each of these points, so that no one physical resource has to be scheduled to service two points in the pipeline. Thus the pipeline naturally ends up with at least 3 separate caches, instruction TLB, and data, each specialized to its particular role. Victim cache. A victim cache is a cache used to hold blocks evicted from a CPU cache upon replacement. The victor cache lies between the main cache and its refill path, and holds only those blocks of data that were evicted from the main cache. The victim cache is usually fully associative, and is intended to reduce the number of conflict misses. Many commonly used programs do not require an associative mapping for all the accesses. In fact, only a small fraction of the memory accesses of the program require high associativity. The victor cache exploits this property by